Is everything clear? Everyone can see? Good. Okay, so the topic, as is written, is Huffman coding. The main theme is greedy algorithms, which we'll continue with. So Huffman coding is a classic example of a greedy algorithm. So I thought I'll show it to you. Also, I mentioned as a historical comment that the Huffman of Huffman coding was one of the first computer science professors at UC Santa Cruz. So this is something that, but although I think he did it when he was in his PhD thesis. Okay, so what is the question? The question is, you want to find the optimal prefix-free encoding for a universe given the frequencies of elements. So think of sigma being, I'm just denoting it 1 to n, but you can just think of it maybe as alphabets, right? So A to Z. And for each letter in the alphabet, you have a frequency, which is how many times it occurs. So you have the text, and in that text, for every character, you have the number of times that character appears. You want to design a binary encoding, a prefix-free binary encoding. So what is an encoding? It just says you take any element, any alphabet, character, and you have a string, right? So 0, 1 star just means strings of variable length. Binary strings of variable length. And no encoding should be a prefix of the other. So if you think about representing every string as the node of a binary tree, right? So if you take any binary tree, so see if I can zoom out. Every node in a binary tree has a string representation, right? Because to go left is 0 and to go right is 1. And if you follow the path down, then you get a string representation for every node. Importantly, observe that if you take any two leaves, neither representation is the prefix of the other, right? So the only way you get a prefix is if you have a node and its ancestor. That's a prefix. So if you take the leaves, then you get a prefix-free encoding. Is that clear? That's a prefix-free encoding. So now what we have is for any binary tree, where the leaves are represented with characters, we have an encoding. Is that clear? So for every binary tree, you have an encoding. By the way, how many of you have already seen Huffman coding? Raise your hand. Okay, few of you. All right. So now what is the length of the total encoding of the original text, right? So we were given frequencies of the elements. We were given frequencies. So for every character, let's say the ith character, you look at the depth in the tree. That is the length of the path. So the depth of C is 2. The depth of D is 1, 2, 3, 4, where I'm measuring depth by edges. And so the encoding of D is 1, 1, 1, 0. And so that the depth of I in the binary tree is the length of the encoding of I. When I multiply that by the frequency, that is the total length of encoding all the I characters. And I'm summing that over everything. So this is the length of the total encoding. And what is my problem? I want to compute the tree that minimizes the length of this encoding. Right? So this is basically like a compression scheme. And indeed, if you can code this up, this is like, think of it as a very rudimentary form of zip, like when you're zipping a file. Because what you could do is you could take a file, you look at every character, compute the frequencies, find this binary tree, and then you get an encoding. So the encoding process is to replace every character by the string. The decoding process is to do the opposite, and the decoding is a tree walk. Because it's prefix-free, if you actually follow the tree, like if you start from here, you follow 0, 1, okay, you hit E, you remove it. Then you follow 1, 1, 0, you'll get N, so on and so forth. So the tree walk basically is the decoding process. Right? So the encoding and decoding process, once you have the tree, are fairly straightforward. It's a good programming exercise, but that is not our point, the question that we are interested in is how do we find the encoding that minimizes the length of that? Okay, so I'm just going to take a look at the screen as projected. So hopefully people over Zoom, the few of you that are there, hopefully you can see and hear what I'm saying. Okay, very good. I'm just going to spotlight this.
Looks good, Professor.
Okay. All right. Okay, any questions up to this point? No. So what is the idea? The idea is actually a greedy procedure. Okay, so yeah, but it's clever. Instead of, you have to think differently. Your natural instinct is to take the most frequent character and put that high up in the tree. What this says is, and that will be an assignment question as to why that doesn't work. Here you actually do the opposite. You start with the most infrequent characters and try to put them as far away, which seems like the same thing, but this is the way it works. You take the two most infrequent characters, call them I and j, make them siblings in the tree. Okay? Then you combine the characters to get a new character, a new fictitious character that you can call like ij paired up with a total frequency. You take f of I plus fj, that gives the total frequency. Now you have a new alphabet, one smaller. You also have a new set of frequencies. Although the only alphabet, you only introduced one new character. You remove two characters, introduce one character, which has a frequency, solve recursively. Make ij children of that new character. Does that make sense? Any questions about this? What the algorithm is? Okay, how long will it take to implement this? How long does it take to implement this procedure?
Like n log n.
Huh?
Like n log n.
N log n, why?
If you use a priority queue,
Priority queue.
you're adding, I guess, endings to the queue and removing.
Priority queue, right? The answer is priority queue, exactly. So what do? So I'll just write down the algorithm here. This is an extremely annoying height to write at, right? Like what I need is something at this height or even lower, because then my hand would be straight. Let's see how I can do with this. Okay, so what is the idea? So let me just write out the algorithm. Right, so step one is you initialize a min heap. Right? So a priority queue, a min heap with the characters where the key is the frequency. So I'm going to write this in somewhat of a haphazard way. I don't want to write down like the full recursive procedure and give you the whole pseudocode, but just to write out the idea. So you initialize a min heap with the characters where the key is the frequency. Delete the two smallest characters from the min heap, which I'll call h. Right? So how long does this take? This is going to take O log n. Right? And then what you do is you, so let's say, let me call this I and j. Insert the character that I'll just denote as the pair ij with frequency fi plus fj. Right? This is now the total frequency of that. And then essentially what I'm doing is, okay, so I said it's badly written code. Technically, you keep going back to the second step. So at this point, what you do is you'll recursively solve. Right? Recursively solve with this, which is basically going back to this step. So I'm just going to write this poorly. Recursively solve, make I and j children of the character ij. So this is sort of badly written, but essentially observe that the total running time for these steps is O of log n because you're using a min heap. And you will do this at most n times, right? Because every time you're extracting, you're deleting 2 and adding 1. So you're reducing the alphabet size by 1 in each step. So the total runtime, the total running time is O of n log n. Okay, so that gives the implementation, the greedy algorithm. What is important is to understand why this algorithm works. So I want to discuss the proof of this, because this will be another demonstration of how you prove a greedy algorithm is correct. Okay, any questions? All good? Okay. So let me start with, let me write this out as a claim. I'll just say that the optimal tree is so let me zoom this. The optimal tree is what I'll call a fully binary tree. Not balanced. Full, what this means is that no node has exactly one child. I'm going to leave this as an exercise, but essentially I'll draw out a picture and it'll tell you why. So suppose you had an optimal tree that looked like this. I'll make the leaves squares. Why is this not optimal? Yeah, go ahead. You could move this, you could remove that, and you could move it there. And thereby you would decrease the depth of one of the characters and preserve the depth of every other character. So you must be increasing your you must be reducing your objective value. So whenever you have a node with only one child, you can always take a leaf from somewhere else and plug it in over there. Does that make sense? Yeah.
Your depth is not changing, right?
Sorry?
Your depth for the tree is not changing, right?
For which is not changing?
Depth for the tree.
The full depth of the tree might not be changing, but individual leaves are changing. Remember that the objective is the sum of fi times di. So if I can reduce one of the di's but keep everything else the same, I'm going to reduce my total depth. Right? So you're right that the total depth is not changing. This argument is not yet complete, but you could complete this argument. There's one case where actually, if you have a tree that looks like this, suppose that was your tree, just that. Well, then what you would do is you would just replace this by a leaf, right? So you can move things up. So in all cases, when you have a node with one child, you can reduce the depth of, you can reduce the depth of, well, you can reduce the encoding length of one character while preserving the encoding length of all characters. This is key. This is how you prove optimality, because you might reduce one and increase another, and then you can't prove optimality any longer. Does that make sense? Now, the reason I want you to formalize this, but I'm going to use this idea and I'll give you a formal argument for why this is true. Okay, any questions? Okay, good. It's much better in person. Now I can see your faces, and I can at least guess whether you're understanding or not. And the secret is not looking at whether people nod or not, because students always nod. No matter what you say, they will nod. When they don't understand, they will nod. But their eyes glaze over. And maybe I should wear my glasses just to get a better sense. But usually I can see eyes glazing over. Like then their eyes will they'll just do this strange thing, and then you know that they don't understand. So it's very hard to fake that. All right. Okay. So how are we going to prove this? Okay. We will prove an intermediate claim. And with this intermediate claim, then we can get the final proof. Now, what is the claim? It says, consider the two most infrequent characters. Right? Those are the ones picked, so I'll call them maybe I and J, right? There exists an optimal tree, then optimal encoding tree, where I and J are siblings. Okay, so if I can prove that, then hopefully you start seeing why this algorithm works. Because if I know the two nodes are siblings, then imagine removing them and just replacing them by their parent, and their parent has the total frequency as a sum of the children. Okay, questions about that? This people are not so convinced about. See, your eyes are now glazing over a bit, right? Okay, let's first prove the statement. Okay, so before we write the formal proof, what is the picture that you have in mind to prove the statement? Why is it that the two most infrequent characters should be siblings? Okay, so where should the most infrequent character lie? Probably at the most depth. Why should the other character be why should the next infrequent be a sibling of that? I'm sorry, go ahead. Yeah.
Since they have to have two children,
Okay.
then you have another more frequent character at the bottom that you could swap with a more infrequent one.
Essentially, because you know that the tree is a fully binary tree, every leaf has a sibling. So if you look at the maximum depth, that has a sibling. So there are two nodes at the maximum depth, right? Assuming the alphabet size is at least 2, which you can assume, right? So unless the tree is a single node, the tree has at least 2 leaves, then leaves must basically, you have to be a little careful here, but essentially, every time you have a leaf, you look at the sibling. A sibling must exist, right? It could be something like this. A leaf may have a sibling that is not a leaf, but it still needs to have a sibling. And if you look at the maximum depth leaf, its sibling must be a leaf, because if it was not a leaf, then there is something else that is of even more depth. I will write this down, but I want you to see the picture. So you know that the maximum depth leaf has a sibling that is also a leaf. And so it makes sense that the two most infrequent characters should be represented by that, because if they were not, then you could swap. Remember, you can always swap the leaves. You can swap the characters at leaves. Does this logic make sense? So it's similar to this, right? It's all this sort of swapping nodes. So back in the day, this was enough to basically get a master's thesis, but not anymore, right? This was maybe about, I don't know, 40 years ago, maybe 30 years ago. No, 40, maybe 50 years ago. So I'm dating myself. All right. Okay, so let's write this proof now. So the way that you would prove this is usually by contradiction. Okay? You say, okay, suppose not. Suppose not. So I and j are not siblings. Okay, and let f of I be less than equal to f of j. This is without loss of generality. WLOG means without loss of generality. I mean, one of these obviously is the minimum, just call it I. Okay, so f of I is less than equal to f of j. So I is the most infrequent character. Okay. Okay, now what we'll say is let, okay, so it's going to say, no, you're right. If there exists a character k such that the depth of k is strictly greater than the depth of I, then we can swap k and I in the tree and preserve optimality. Maybe even increase it. Okay, why? Before the swap, the objective, the total, I guess the length, is equal to summation over all I. No, let me not use I, j, k. I'm going to use a different symbol, L. F of L times d of L. After the swap, the length is equal to, so L not equal to I or k, f of L dl, plus, now what you did is you did a swap, right? So f of I is going to have the depth of k, and k is going to have the depth of I, right? You swap those things. That's what the swap does. Does this make sense? And observe that this quantity here is less than equal to f of I d of I plus f of k d of k. Does everyone see why that is the case? Should I work that out? Yeah, you see that, and this is because I is the smallest. Yeah, okay, maybe not convinced. that you see why this is true. Okay, so let's just write that out. Okay, like a small proposition. Let's just write out the proof so that everything is perfect. So the proposition here is f of I d of dk plus f of k di is less than equal to f of I di plus fk. So the proof is, think of what is the best way to do this. Well, this is sort of illuminating. Do it. Okay, suppose not. So then f of I dk plus f of k fk di is strictly greater than fi di plus fk dk. Okay, that is equivalent to saying fi dk minus di is strictly greater than fk Am I doing this the right way? Okay, yeah, good. Okay, now, important. Why can you cancel these things out? It's greater than 0 because dk is greater than di. This is important. Otherwise, when you cancel out, you'd flip the sign. So dk is greater than di. Because dk is greater than di, you can cancel these things out, implying f of I is greater than f of k. But that's your contradiction. I was supposed to be the most infrequent character. So contradiction. While this statement is not hard to prove, it's also not obvious. Like, you have to be careful to prove it formally. So what you've shown is that fi dk plus fk di is less than equal to fi di plus fk dk. So when you did the swap, you have not increased your length, which means if you were optimal before, you're still optimal. Okay, why did I do all of this work? I did all of this work to show that if there is a character at a depth that is larger, I can swap them and preserve optimality. Is there a situation where this is actually equal? Is there a situation where these are equal?
The frequencies are the same?
Which frequencies?
The K and F.
Can fi be equal to fk? Can f by equal? Yeah, yes, no? It's possible there could be multiple characters that are all equally infrequent. The most infrequent may be attained by multiple characters. So you could have a swap, which is why I have to be a little careful, right? I mean, it's not saying that it is possible that even though I is the most infrequent character, there exists a tree where I is not at the maximum depth. I'm going to say this again, and then I will write it down. It is possible that there exists an optimal tree where the most infrequent character is not at the maximum depth. We're not saying that this has to happen for all trees, but there always exists one where it will be at the maximum depth. That statement I'll write this down. And then so I will write that down at the end. I want to finish this proof, then I will write that down. Okay? So there exists a character. You can swap k and I in the tree and preserve optimality. Okay? So hence, Okay. Hence, there exists an optimal tree where I is at the maximum depth. That's what we've asserted. The claim is there may exist an optimal tree where I is not at the maximum depth. That's what I'm saying. Okay? All right, so there exists this optimal tree where I is at the maximum depth. Oh, okay, so we did all this work and we got there. Now what do we do to complete the proof? So we said I is the most infrequent character. Now how do we complete the proof? Yes? You wanted to show that I and J are siblings. Right? You want to make I and J siblings. I is the most infrequent character. You put it at the maximum depth. Now what? Is everyone following? I'm not getting a confident vibe here. Again, eyes are glazing over a bit. So I'm going to pause here. I want you to ask me questions until you understand exactly where we are and what needs to be done. Let me draw a picture. So you started at some tree. And maybe this tree looks something like this. Right? And I was somewhere over there. What we have done now is we moved I down to that. Now what?
The same could be said about J, right? Since he did it without loss of generality.
Good, but then maybe I'm just going to swap I and J. And I is the second most infrequent. It's not the most infrequent. So actually, no. No, it won't work. Because what if I end up taking J and then trying to swap with I? And J is actually more frequent than I. Does that, you see what I'm saying?
What if you just consider like the new objective minus the old objective if you swap J with I, and then use.
But you don't want to swap J.
Sorry, not swap J with I. Sorry, just swap both I and J with X and Y.
What's X and what's Y?
The two children at the max, two of the max step things that are siblings.
So you're basically proving it in a different way, which is to find the two siblings at the max depth and then swap I and J.
Yeah.
I'm doing it differently. That will work. What I'm doing is morally equivalent. It's actually the same argument, but I'm just doing it differently. I'm just saying, first you move I to the max depth. Now what? Now you want to move J to be its sibling.
Sure.
Why can you do that?
The frequency of J is not more than the sibling.
So why does I have a sibling? From the previous claim. What if I's sibling is not a leaf?
It has to be because
Max depth, right? So I'm stating all of this so that you kind of see how all the pieces fall together, right? Because it has to be done carefully. And every single thing that you prove falls in place in the final proof. Okay, so good. So I is at the max depth. because the tree is fully binary, I has a sibling, and because I has max depth, the sibling is a leaf. Right? So there must be a leaf here. And let the character in the sibling be k prime. I'm calling it k prime because I previously used a k over here, so I call it k prime. F of k prime is greater than or equal to f of j. Right? And k prime is at max depth. So we can swap j with k prime and not increase the objective. Does that make sense? And the argument is, again, you have to use the proposition. Right, this proposition which does the swap is key. Right, the proposition that does the swap, you use the same argument again. So I don't want to write that argument all over again, but essentially you have to use this proposition. Okay, so does that make sense? So any questions about this?
What if k prime has a frequency that is less than something else between k prime and, like, in the depth between I and k prime?
I'm sorry, say that again?
So, like, you swap j and k prime,
Mm-hmm.
and then let's say, like, the depths are at least, like, 2 apart. Then what if, like, in between there's one that's less or more frequent than k prime? Now it's still not.
It's a good question. The thing is, that actually cannot happen in a tree that was optimal. But you don't have to worry about that because you assume this tree was optimal and you did a swap that's only decreasing the average depth.
Right.
What you're saying is, you're saying like j might be somewhere here. And you're saying, oh, what if you swap these two and actually there's something else over here. So k prime should have gone there, not go that high up.
Right.
If this was the case, this tree to start off with was actually not the optimal tree because j prime was too high up for being so infrequent.
Okay.
Except the thing is now, you could say, why don't I have to prove that? So this is where it's interesting. You assume optimality of a tree, and then whenever you do swaps, you know that you will never, as long as you don't increase the objective by a swap, it's a safe swap. So you start with something that's optimal and you keep doing safe swaps. Does that make sense? You know, your point is well taken, but essentially, implicitly, that tree was not optimal to start off with. But your proof doesn't. So this is actually a deep point. This comes up a lot in proofs of optimality, which is, in some sense, you're not really using something specific about the structure of the optimal thing. All you're doing is you're defining the notion of a safe switch, and you just keep doing safe switches to get a property. Does that make sense? Okay, so all right, so far so good. So what we have right now is this claim over here. Consider the two most infrequent characters. There exists an optimal encoding where I and j are siblings. And now you can kind of see that with this, the whole proof should come together. Because the moment you know that two characters have to be siblings, you kind of treat their parent as a character, and you just solve recursively. That's the idea. So I will write this down, but that's the idea, right? Once you know that two characters will be siblings, then what you're trying to do is basically optimize the remaining tree. So let me draw that again. So if you know these two are siblings, you could say, okay, now what I need to do is just to deal with this tree here. And this tree has one fewer leaf. And the leaf that corresponds to these two is really the parent node. So it's almost like I treat that as a leaf and then solve for that problem recursively. And then just stitch these two on top. Okay, again, I'll do it formally, but let's. Questions? And you'll see that essentially, like, this sort of claim is going to keep, is this sort of swapping idea is repeatedly going to appear. Okay, all right, so let's kind of make that argument formal. So what we'll do is, like, we need to state another claim. So the claim is, consider an optimal tree over the alphabet n, where I and j are siblings. Okay? Yeah, go ahead.
I have a conceptual question.
Sure.
So, I don't understand why you can combine I and J as one thing. Are they separate or they have different
Encodings?
yeah.
They do have different encodings. Their encodings only differ on the last bit.
Right.
So if you strip away that bit, then their encodings are actually the same. So, okay, so one way to think of it is, so let's go back to this tree, right? So what is the encoding of this? It's 0, 0. The encoding of this thing is 0, 1, right? So what you know, let's just say that you know these are siblings, but you don't know where they are in the tree. So you say, I know that there is an encoding where the only difference for these two characters is the last bit. But I'm now trying to optimize on whatever is the remaining encoding. So if I look at the encoding after stripping away the last bit just for those two, it's like treating those two characters as the same and creating a new character whose frequency is the sum of frequencies.
But then how would you know once you're like decoding that they're two different characters?
The decoding process, once you construct the tree, the decoding is independent of the tree construction. So once you construct the tree, then you decode. So okay, so here is the thing, like all of these arguments that are being made aren't actually done by the algorithm. The algorithm is simply doing this. So all of this processing that we're doing is only the proof of optimality. It is not actually being done. I don't know if I'm making sense here. Like it's not being done in the algorithm. We're just doing these swapping and all of these to prove that this is optimal. We're not actually going to construct the tree and start swapping things around. Okay, so maybe why don't I write the next proof, and then I think that should clear that up. Okay? So you understand this so far, right? The two most infrequent characters, they will be siblings. So now I say consider an optimal tree over an alphabet where I and j are siblings. So let me say that tree is T. The tree T minus ij. Okay, so what do I mean here? Remove the leaves I and j from the tree. Is an okay, I'm gonna write this in a clunky way, but then maybe it's fine. So the tree Tij, where you remove leaves I and j, is the optimal tree for the alphabet n minus ij union another character. So I'm going to remove I and j. I'm going to put in another character. I'm going to refer to this. Okay, so maybe let me, I'm going to refer to this character. I'll just call it I star. Okay, I'm just going to call it I star, where the frequency of I star is equal to the frequency of I plus the frequency of j. Okay, so I'm almost restating the properties of the algorithm as a claim. But if I prove this claim, then you should be happy, right? Because then essentially the proof will follow. Yeah? This is true for any two of them, right? Because if you take any two of them and you remove it, whatever remains will be optimal for that. It could be that, so say that again, I and j are the most infrequent, you said. No, this is actually true even if, regardless. As long as you know they're siblings. As long as you know they're siblings, then you know their bit representation, right? So, okay, I think so. Let's see. Maybe I'll get stuck, and then we'll know. But I am writing this proof off the fly, so we'll see. I could be wrong. Okay. But I don't think so. Any questions about what this claim is saying? So how do you prove this? Right? So again, what you'll do is some kind of contradiction, right? You'll say, suppose I start with the optimal tree. It's got some depth based on the frequencies. And suppose when I remove the leaves, the tree that's remaining is actually not optimal. Right? Then what I could have done is, I could have taken the optimal tree for this alphabet, stuck I and j as the children of I star, and actually reduced everything. So that's the argument you want to make. You want to say, suppose I start with the optimal tree, I removed I and j, right? So I did this. Okay, so let me draw a picture here, right? So I have some tree. It could be anything. All I know is that I and j are siblings. They're not even at the maximum depth. They could be anywhere in this tree. If I remove these, then this becomes a new leaf. This is this I star. If I could get a tree that was better than this tree, suppose instead I got some other tree where I star was down here, and this tree was better than this tree here. Well, then I could have gone and put I and j over here, and my overall objective would have improved. The reason for that is because the frequency of I star is exactly equal to the frequency of the sum. But this is the argument. Now, does that answer your question? Yeah. Yes, no? Okay, so let's go through this proof now. I mean, the way that you construct these proofs is always you do some kind of proof by contradiction. You say, suppose it was not optimal, then you could have improved the objective value. And all the proofs on greedy always go in this form. It sort of says that if you made a different decision, or rather, if you took a solution that was not greedy, by making a change to its decision, you could have improved the objective. And so this is the style of argument that you would have seen in the knapsack, where it's like saying, okay, choose the other item and then you get an improvement. Here it's, this proof was also, do a swap and get an improvement. Right? So this is sort of the style of proof that you always have for greedy. That's why I say that for greedy, coming up with the algorithm is easy and proving is hard. And with dynamic programming, coming up with the algorithm is hard, but the proof is almost obvious because literally the recurrence is the proof that it's correct. Right? Okay, so let's try to go through this proof. So consider the optimal tree T, which minimizes which minimizes the sum over I and n of f of I, the depth of I. Okay? Now, the tree T minus ij has the objective. Okay, now let's look at this. If I remove these two nodes, and just think about the decoding procedure. How many times do you encounter that node when you decode? Does that make sense? So when you decode, you're going to encounter this node every time you do the tree walk. How many times do you encounter that node when you decode? If you were to decode the entire, so consider the original tree, right? How many times do you encounter that node?
Twice.
Sorry?
Twice, right?
When you're doing decode just once.
No, but totally, when you decode the entire text. So you encounter this leaf I, f of I times.
Oh, I see. F of I plus F of
You encountered exactly f of I plus f of j when you decode. Because you're going to go down to that, you're going to follow this path down f of I times. You follow this path down f of j times. So it's f of I plus f of j. That is exactly why you replace it with f of I plus f of j. I don't know, does that answer your question now more? Like, this is why when you remove it, you're saying that this is this new character whose frequency is the sum. Okay? So the tree T minus this has an objective value of, okay, so this is bad notation on my part. Okay, f of L d of L. So L not equal to ij of f of L d of L plus f of I plus f of j d of I minus 1. There's a minus 1 because essentially the depth is 1 less. So this is the optimal cost of that. Now suppose there is a tree which I'll call T prime on the alphabet, on this alphabet, n minus ij and I star with lower objective. Okay, so the depths in T prime are denoted by, I'll just call it D prime. So the objective is now L not equal to ij, f of L d prime L plus f of I plus f of j d prime I star. Right? This is the objective of this improved tree that I got. So because I have this one character with frequency fi plus fj. Now create a tree T double prime. That's the nice thing about primes. You can just keep adding them on to get more and more variance, right? So T double prime, where I and j are children of the leaf I prime in I star in T prime. So how did we go? We started with T. This is T. I and j. That's what T was. This tree over here, which is T minus ij, is the same tree, except that internal node becomes a leaf. So there's this process where you take away children and you get a new leaf. And here we reverse that process. So T prime has some thing here for I star. And T double prime is you basically make ij children of this node that was labeled I star. Right? So I'm just reversing this process here. So I now consider T prime. The T prime is now a tree over the full alphabet. Alphabet is n. So what is the objective value of T double prime? Well, for L not equal to ij, it's f of L d prime L. Now what is the depth of I and j? It's exactly the depth of I prime plus 1. So I get plus f of I times d prime I star plus 1 plus f of j d prime I star plus 1. Okay. Now let me move this thing around. I get the summation L not equal to ij f of L d prime L plus f of I plus f of j d prime I star plus f of I plus f of j. What is that quantity there? If you look through this, if you look through it, you'll see it. You'll see that it occurred somewhere else. This? Fi plus fj is f of I star. That is correct. But okay, so what you want to observe is this, the objective of T double prime is the objective of T prime plus f of I plus f of j. The objective of T prime is strictly smaller than that. And then if you add f of I plus f of j, you'll cancel out the minus 1 over there, and you end up with the objective of T. So you actually started with objective of T prime. T double prime is strictly less than the objective of T. Contradiction. Okay, so this is how you have to chain these things together carefully, right? So this is objective of T. This is the objective of T minus ij. This is the objective of T prime. And this is the objective of T double prime. And you kind of relate all of these things to each other until you get your final contradiction. So you see that the actual maximum is not important. Okay. So just going to write this down here. So this is equal to the objective of T prime plus f of I plus f of j. By assumption, this was strictly less than the objective of T minus ij plus f of I plus f of j. This is important, strictly less than, because there is a tree T prime which had lower objective. That's how I get my contradiction. What is the objective of T prime? I'm going to write this expression down. I'm going to add fi plus fj to it so that minus 1 gets off. Then I end up with T prime. So you see how the fi plus fj is crucial, because you subtracted it out and then you add it back in. Okay? So let me just write this out, and then we'll pause for a few minutes and take a break. So this is the summation L not equal to ij f of L d of L plus fi plus fj di minus 1 plus f of I plus f of j. And so when you take this and you sum it all together, you just get the summation over all L fl DL, because I and j have the same depth in the final tree. And this is the objective of t. So you started with objective of t double prime, and you ended up with something being strictly less than the objective of t. Okay, I don't have enough space to write contradiction, but that's the contradiction. I'll write it down here. Contradiction. I mean, there's a reason why these proofs are sort of verbose, but that's because they're really pinning down every little thing. Okay, so now when you put this together, you consider the two most infrequent characters that exist in optimal encoding tree where they're siblings. And then you say that consider a tree where I and j are siblings. If you remove I and j, you have an optimal tree on what's left with fi plus fj. And now the proof is complete, right? Basically, you're just doing induction over this argument for the final proof to prove that the algorithm is correct. Okay, so these are the pieces for that. I don't want to write down the induction because it's a straightforward thing, but this is the idea. Questions? I can't imagine all of this was crystal clear, so please ask questions. And this is a good time to take a breather. We have about half an hour left. So if you want to get up, stretch your legs, you want to step out, go ahead. You want to talk to your friend, go ahead. It's fine. Or maybe you want to see your phone because you haven't seen your phone for the past 1 hour and you're getting antsy, go ahead. It's fine. But you can also ask me questions in the meantime. I can answer. Question?
Do you think that in the beginning you can draw a quick example of this algorithm?
Of the Huffman?
Yeah. I mean, I'm not sure how. I'm kind of confused about when we combine the two siblings. I'm not exactly sure what we mean by combining them and making them.
Okay, so yeah, we can do an example. We can do an example. It's funny, there's a joke that came to mind when you said draw an example. So I don't know if you've heard of Alexander Grothendieck. The rest of you can talk, it's fine. So Grothendieck was a very famous mathematician, probably one of the most prominent algebraic geometers of the 20th century, worked very abstractly. So he was giving a talk, and he said, let P be a prime, and he started doing all of this stuff, right? And some student said, I'm sorry, can you give an example? I just don't understand. He said, yeah, just take P equal to 57. 57 is not a prime. That's the complete joke. Okay, that wasn't that funny, but whatever. So, but 57 is referred to as the Grothendieck prime for that reason. No, what do you mean?
I'm replacing the 2 with a third new character, and I want to maximize the frequency with which it appears so that this encoding remains the optimal. Do we know anything about that?
No, but isn't it Huffman coding? I don't understand. What do you mean by maximum? I mean, it's exactly what it's doing, right?
Here the condition is exactly fi plus fj.
Oh, you mean under what frequencies would it still be a pro?
If you are wrong, would be everything at a depth higher than that should.
I mean, I think all the constraints are basically linear constraints. So you could probably write an LP. You could say that, look, if the frequency of this thing was close enough to Fi plus Fj, I guess, are you asking under what frequencies of I star would this thing still be optimal? Yeah, that I think essentially small perturbations of that you think should not make an effect. But how much? So essentially it's all about probably the relative ordering of those things. So as long as the relative ordering is preserved, I think it'll probably be the same.
Is it of value?
Well, it's a good exercise. It's looking a lot like the Chebyshev sum inequality, which basically does these things, right? What you have over here is a dot product. I mean, this thing is a dot product. And what you're asking is, when I permute the order, then how does the dot product change? So the Chebyshev sum inequality tells you things about when the dot product is minimum or maximum, although it's still not entirely, but this is structured because, so it's, but I think that essentially as long as the relative ordering does not change, that's not true actually, no, that's not true. It's not the relative order, it's more than that. Because the sums of things are relevant.
But the relative ordering is sufficient.
No, because I don't. Actually, no, because what the Huffman coding algorithm tells you is that sums of frequencies are relevant. And so even when the relative order is the same, the sums may behave differently. I mean, probably if all sums are also have the same relative ordering. So I'm pretty sure that if you take two instances where the relative ordering of all subset sums is the same, then it will be, but I think you need that. If that changes, then the tree might change. Okay, not entirely. Maybe some. It's a good question. I don't think it's an obvious answer, because there may be certain subsets whose ordering is irrelevant. What's only relevant is the minimum at any stage. So. Oh, sorry, someone in Zoom said the screen is blurry. But unfortunately, that's about the best I can hope for.
No, now it's good, Professor. It just got blurry for a couple minutes.
Okay, all right, okay, all right.
Thank you.
So, can you hear me?
Yes, perfectly.
Okay, all right.
Thank you.
All right, let's continue. So, how many of you want to see an example of Huffman coding? Like, would that help? Raise your hand clearly so that I can actually see how many people. Okay, there's enough of a cohort that wants to see an example. So why don't we just go ahead and do a small example of Huffman coding? So I don't know. Let's do it with 6 characters. Okay. So let's say the characters are A, B, C, D, E, F. Yeah, when you switch it off, actually, it does better sometimes. Okay, okay, so F was a terrible choice because F is frequency. So, yeah, let's do Greek, exactly. Especially with COVID, we should do Greek, right? Alpha, beta, gamma, delta, epsilon, and phi, right? Let's not do Omicron, right? Let's not go that far. Okay, so, all right, so what are the frequencies? Someone give me some numbers. Some numbers. What is the frequency of alpha? 10. 42, of course. 2. 69. Okay, what next? 1. Okay, there it is. So 10, 42, 2, 10, 69, and 1. Okay, so what is Huffman coding going to do first? It's going to remove the 2 minimum. So the 2 minimum. So what are the min at this point? It's going to be gamma and phi. Right? And then you're going to end up with alpha, beta, delta, epsilon. And this new thing that I'm just going to refer to as, I'm just going to pair them up so that we know that they're together. 10, 42, 10, 69, 2. Okay, so then now what are the min? 3, I'm sorry, 3. So now we remove the 2 min, so we remove alpha, and you remove gamma phi. Okay, so you have beta, delta, epsilon, that's 42, 10, 69, and alpha, gamma, phi, sorry, that's 13. All right. Now let's do the min again. So now we get delta, and we get this alpha, gamma, phi. So you see that you're basically collecting subsets of characters. So beta is now 42, epsilon 69, and this is going to be 23 for this large thing that now I'm just going to call S, because I don't want to write this thing over and over again. Okay, now we do the min again. And so we have beta and S. And so we'll get epsilon, beta S, 69, and we have 65. Okay? Now you only have 2 characters left. Okay, so now that you have 2 characters left, what is the tree that you're going to give to these 2? Yeah, so you encode one of them as 0 and the other one as 1. Right? Okay, so that's the root. There is epsilon. Sorry? The laptop is in the way. Okay, so the laptop I don't want to move. I can move this up. Yeah, okay. I don't know. Usually this automatically will focus. All right. Okay, all right. And then this is going to have one child, which is this beta S. The reason I'm not making it a leaf is because this is going to become an internal child. So wait a second. Okay, right. So beta and S, because we combined beta and S over here. Now we're going to make these the children of beta S. So we'll put beta over here and put S over there. Now we could have swapped those, it doesn't matter. And then what we're going to do is S was actually alpha, delta, and this thing over here. So it was alpha, and then this, alpha, gamma, phi. You'll see that in this case, the tree is a linked list.
It's delta, not alpha.
Sorry, delta. No, wait. Oh, this is delta. That's alpha. Sorry. Okay. Delta. And so then the children of that was alpha and then gamma phi. So this becomes alpha. Then you add an internal node, gamma, and phi. So in this case, essentially the dumb algorithm worked, which is, you can see the ordering of this is exactly the ordering of the frequencies. Because your collective choice of frequencies was a very poor example of Huffman coding. Essentially, that's what it boils down to, right? So what it did was, because epsilon is so frequent, it just made that encoded with. So what's interesting is that the encoding of epsilon is just 0. And every other thing. So let's actually see what the encodings are, right? So the encoding of this is 0. The encoding of this was 1, 0. This was 1, 0, 0. 1, 0, 0, 0. And no, I'm sorry, the other way around. 1, 1, 0. 1, 1, 1, 0. 1, 1, 1, 1, 0. And 1, 1, 1, 1, 1. So the encoding ended up being a unary encoding, essentially. Like you just look at how many 1s there are until you get to the next 0, and that tells you which alphabet it is. If things were more evenly balanced out between these, things would have become more interesting. I'm trying to think about if there's a quick way of doing this. So I guess
If epsilon is 22, then like
if epsilon was 22, then maybe at this stage, like if you wanted, so let's say that epsilon was actually, I was thinking epsilon being maybe, so if one had changed these to make this something like 8 and 9, then this would have become, okay, so you have to play around with these frequencies, but what you could have done was played around with it so that in one stage gamma delta gets combined, in the next stage gamma and phi get combined, here alpha and delta get combined, then the tree will start looking more interesting. Like one could have made, one could have reordered these so that you pair up one pair and then you pair up another pair, something like that. Right? I think, that would have happened. If you made this 8 and 9, then this would have become 17. Then at the next stage, the min are alpha and delta. Then you would pair those together, and then you would end up with an encoding which would be much more balanced. Questions? Maybe I should do more examples. So, okay, another mathematician joke. Maybe this will be funnier. So a mathematician explains a proof on the board. At some stage he said, this is trivial. And then he goes from one step to another. Then a student stops and said, no, can you explain that? And then he stares at it and he starts thinking about it. And he's pacing up and down. After 5 minutes he says, oh, of course it's trivial. And then he moves on. So, okay, maybe that was funnier, right? All right, so we have 10 minutes left. So naturally, this is not enough time to finish anything, but it is time to start something. So I want to do the last greedy algorithm that we'll be discussing. And this is a classic, which is the minimum spanning tree. Okay, so I'll just introduce the minimum spanning tree. The next lecture, maybe I'll just mention it again, and then we'll do minimum spanning trees. This is a classic graph algorithm, which is again a demonstration of of how greedy algorithms are an example of a greedy algorithm. So what is minimum spanning tree? So consider a weighted graph G. And so we'll just, the weights, let's for convenience just consider it to be a non-negative function, although negative weights will also work. So the weighted, connected, undirected. Okay, so you have your tree. So the usual example given, and this does occur, is maybe you're building like your cable network or your power network, right? And so you have your various cities. And so there is some cost to putting down an edge over there, either a road or a cable or whatever. So there's a cost between any two. That's what the weight function tells you. And you could think of E as like the set of edges that are allowed. Like you can't afford to maybe connect through things that are far away, but close by you want to put an edge. And so what you want to do is basically put down edges so that every node is part of the network. Put down a bunch of edges so that every vertex is part of the network, and you want to minimize the weight of the edges that you're putting down. Does that make sense? So you want to put down a set of edges, and you'll see that it's a tree on the vertices, so that every node, every vertex is part of this tree. And it's connected, right? So there's one connected structure. And you can think of like the weight is like the cost of putting down that edge. So you want to minimize the total sum of costs. And this is called the minimum spanning tree, because what you're constructing is called a spanning tree. It's a tree that spans all the vertices, and it's minimum because you're minimizing the weight. Okay, so this is called the minimum spanning tree. It's a classic optimization question. And it's one that sort of started off with, of course, a lot of thinking about telecommunication networks and putting things down, yeah?
So is every node connected to every other, and then you're just like selecting edges basically?
Yeah. No, it's not a clique.
How do you know the weight?
The weight is provided to you, right? The weight is part of the input.
Every pair of nodes has a weight.
No, well, sure. You could imagine that if there's no edge between them, the weight is infinite. So in which case you don't like, there are two cities that you just can't afford to connect. But you generally don't want to represent it that way. You represent this as an adjacency list because you don't want to store all pairs of nodes. So often you have an adjacency list, and then you're solving a minimum spanning tree problem. Right? So this is sort of an infrastructure type question that comes up a lot. So let's do this again. What is a spanning tree? A spanning tree, T, is a tree on V using the edges of G. So this is, again, it's connected. It's not a forest, it's a tree. And in general, when if your graph was not connected, it's called a minimum spanning forest. Because for every connected component, you would build a separate tree. So the spanning tree is a connected tree on V using all edges. It's basically, you can think of it as, it's a subgraph of G involving all vertices. It's a subgraph on G involving all vertices. And this subgraph is connected. So it's actually a connected subgraph on G involving all vertices. Okay? So for any set F of edges, the weight of F is just defined to be the sum over all edges of the individual weights. Sort of the obvious thing that you would expect. It's just saying that if you want to Sometimes this is also thought of in terms of buying these edges. If you want to buy these edges, then this is how much you have to pay. You have to buy each edge. And there are more fancier versions where this cost might not be linear, it might be something else. Someone might have complicated pricing schemes, and these things come up a lot. Lots of problems sometimes under the hood are like a minimum spanning tree problem. So let me just sort of state the problem. And again, you'll see that this is phrased as an optimization problem. You have exponentially many solutions, and you want to find a solution which has some minimum objective. So the problem is, find a subset F of edges such that F forms a connected graph on all vertices, right? That's what it means to span. It's connecting everything such that F forms a connected graph on all vertices, and the weight of F is minimized. Now, I said it's a minimum spanning tree, although the problem doesn't say tree anywhere. Why is that? Yeah?
Since all the edges are positive, if you had a cycle, you could just get rid of an edge and it would be a lower, or at least maybe not lower, but I don't know, they're all positive. Okay, it would be lower.
They're all non-negative. Sorry, this means like non-negative, right? So this keeps things simple. So again, this is a claim. It's a good exercise that the optimal F, or actually instead of the, I'll say any optimal F forms a tree. Because if you actually had something, if you had a cycle, you could just delete one of the edges in the middle and things would still be connected because it's a cycle, right? So you can get from anywhere to anywhere and you still have your tree. You still have like everything that was connected before is still connected. So the problem is to find the minimum spanning tree. Okay, so I won't write anymore, but what I'll say is essentially problems of this form, you can now kind of make it fancier. Okay, so what if you wanted to get a subset of edges where maybe one of the edges could fail? What if you wanted to get a subset of edges where two of the edges could fail? These are robust versions of minimum spanning tree. And indeed, I don't know, when was this? Maybe this was before many of you. Like about a few years ago, like half of the Northeast lost power because there was one power line that failed. One power line in New York failed and it took down half of like the Northeast. So essentially what this means is the power network was not resilient because one edge failed and things got disconnected. So it's natural to ask questions of what do you do when some edges will fail? So this is just saying just make everything connected. But these kinds of problems people study that even now on the power network where they'll take the power, treat it as the power grid, treat that as a graph, and then try to solve these problems. And sometimes you can solve the opposite problem, which is suppose you're an attacker, which of the edges should you remove to disconnect the network? Which I think, this is one of the earliest citations to this kind of problem. There's actually a picture from, I think it was like, it's the height of the Cold War. So maybe in the 60s, there was a picture of the Soviet rail network. And what US scientists were studying is which of these do we need to, if we had to destroy some of them, which should we destroy to basically separate things? So a lot of these questions also basically have this history of, you can look at this as almost like two players. One player is selling edges, one player is buying edges, right? And the person who is buying edges wants to minimize their cost. So these sorts of optimization questions are really like the root of many, many things that people do. And a place where a lot of this has made a comeback these days